Good afternoon, and welcome everyone to this first webinar for the RS4C project. So today the goal was to give some notions of remote sensing for those of us who don't have as much experience with remote sensing, but still are involved with a project that deals with remote sensing. So I'll be giving a short presentation. Of course, it's going to be a bit, it can't be too much in depth with the short time we've given these presentations. I'll give a short presentation, then Elga will give a short presentation, and then we'll have an open Q&A or discussion. And the idea is that anyone can ask their questions, no matter how basic or maybe even a bit more advanced they are, to see if anyone else in the project also has some of these expertise to learn from each other. And everyone will be, of course, welcome to answer. Before we start that session, I'll briefly introduce it again. So I'm just going to start by sharing my screen and the first presentation. Okay, so well, I don't think I need to introduce myself because you're all involved in the project mostly. And in this first presentation, what I want to discuss is just some very basics of remote sensing. So what is remote sensing? Why do we use remote sensing? And why do we sometimes not use remote sensing? Go over briefly how remote sensing works. And what are some of the main characteristics that we need to think about when we want to use remote sensing or remote sensing derived products? And finally, just very briefly, how we can find some data and easily take a look at an area that we're interested in. After this, Elga will give a short presentation as well on some applications that we can do with remote sensing to answer a bit the question, what can I observe in the Earth system or particularly in water with remote sensing? So to start, what is remote sensing? So remote sensing can be defined as the science and art of identifying, observing, and measuring an object without coming into direct contact with it. So this is, of course, a very general definition. And with this definition, we can say that we perform remote sensing every day. So we use our senses, we take a photo. We're not always coming into contact with the things that we're observing. However, when we're talking from the hydrological or earth science perspective, what we're looking at is always, or typically, the Earth, and we're using observations from drones, planes, and satellites. So a lot of the information I'm going to give in this presentation is more linked to satellites. It's mostly what I work with, and it's also data that's sort of openly accessible and easy to obtain no matter where you are. However, it's good to know that drones are more and more used. Some of our colleagues in the team in Ethiopia will be using some as part of this project. And because the cost of operating drones has fallen a lot, they're more and more commonly used for different applications. So why do we use remote sensing? As you know, it can be difficult to collect in situ data. So there can be some practical reasons. So it's costly to install some networks or to go to the field. It can be very difficult to access some areas. It could be because they're remote. Perhaps it's conflict area, so it's dangerous to go to. And even if I collect data in the field, there's not always a good data distribution network behind it. So if I collect data from a specific area, and then you go do a field study for that area a few years later, there's not often a good way for me to get this data out into the world so that the next person can use it. There's also some political reasons that it's difficult to get data. So for instance, data can be there, but it's classified for various reasons. There can be issues with competing users who don't want to share data, conflicts of interest between people who collect the data and people who might want to use the data to advocate for something else. So it's not always easy to get the data for these reasons. And remote sensing can help us to overcome some of these limitations. So the satellites are, of course, very costly, but we're not the ones directly paying for that when we make a study. So we have access to a lot of open access data. When we're talking about satellite data, we can get access to data from any area without having to physically go there, which is very helpful, and so on. Beyond that, so beyond the reasons that it's difficult to get in situ data, remote sensing also gives us a completely different type of data than what we can get from in situ data, which has its advantages and disadvantages. But one advantage, for instance, is that this image is meant to represent, for instance, a river gauge network. So each dot would, a precipitation gauge network. So each dot would be, for instance, one precipitation gauge. And even if you have a quite densely instrumented area, you'll always have gaps between this point data where you don't necessarily know what's going on. Whereas with remote sensing, we'll get a spatial data set. So that's why we're interested in remote sensing. So it can come to help us in areas where we can't get the in situ data, but also it can give us a new type of data which we didn't really have access to through other means. So after this brief introduction on motivation, we're going to look a little bit into how remote sensing works. So the general principle of remote sensing is that we have instruments mounted on the satellite, or as mentioned before, drone or plane, which is going to measure energy which is reflected or emitted by the Earth in different parts of the electromagnetic spectrum. So I'm going to drill a little bit more into this sentence to try to explain what this really means. So the first part of the sentence, we have energy if reflected or emitted by the Earth. So where does this energy come from? Essentially, we have two big categories of remote sensing depending on where the energy comes from. So we have one which is called passive remote sensing, where the sun is the source of energy. So the sun emits energy, and this is reflected by the Earth's surface. And our satellite is going to capture this energy reflected by the Earth's surface. Another portion of the sun, which is emitted by the sun, is going to be absorbed by the Earth and then re-emitted in the form of thermal energy, and this can also be captured by the satellite. And in this case, we call it passive because the instrument isn't emitting any energy, it's only capturing the energy reflected or emitted by the Earth. Another source of energy can be from the satellite itself. So in this case, the satellite will be emitting energy, and this will be reflected, or a portion of it will be reflected by the surface of the Earth, and we'll again measure, in this case, the reflected signal from the surface of the Earth. So if you want to conceptualize this a bit in terms of daily objects, we can think of passive remote sensing as photography. So if we take a photograph in a room, we'll be capturing the ambient light that's reflecting off the objects, and our camera will just be capturing that reflected energy. However, if we take a photograph in a dark room using flash, then our camera will be emitting the light source itself and will be capturing the reflection of that emitted light source off again of the objects in the room. If I look at the next parts of the sentence, we're looking in different parts of the electromagnetic spectrum. So for those of you who work with remote sensing, you're dealing with the electromagnetic spectrum every day. And for others, you might not realize it, but you're also probably a bit familiar with it. So the electromagnetic spectrum it's defined as the range, essentially, of all types of electromagnetic radiation arranged by wavelength. So in the left-hand side image, we can see the image here gives us, for all the different wavelengths, the names of the radiation that we give when they're in the different wavelengths. So you probably recognize some of these names. So for example, X-rays or UV, we hear about these frequently also, and those are quite short wavelengths. And then we have energy or radiation with longer wavelengths, for example, radio waves that we use for radio signal and the FM or AM bands. And these on this right-hand side have a longer wavelength. So why are we looking in different parts of the electromagnetic spectrum? So the sun itself emits electromagnetic radiation or energy, And it doesn't do this in a single wavelength. It does it over a range of wavelengths, which are represented in the image to the right. So we can see that the sun emits from about the ultraviolet part of the spectrum and to the thermal part of the spectrum. So what we see represented on this graph is the amount of energy that is emitted by the sun for different wavelengths. So we can see we have a lot of energy in the visible part of the spectrum. So this is why we have, for example, this is why humans have evolved eyes that can see in this part of the spectrum, because it's where we have a lot of energy or electromagnetic radiation surrounding us in this part of the spectrum. So when we work with remote sensing, we work typically through this range of radiations represented here. So next, we're going to look a bit at why we don't only work in this visible range of the spectrum. So how do we use remote sensing to get information, and what kind of information can we get from different parts of the electromagnetic spectrum? So a good type of remote sensing to use to illustrate this is called multispectral remote sensing. So multispectral remote sensing, the name multispectral means that we're measuring energy in multiple parts of the spectrum. And some of the most commonly used satellites, you've probably heard of the Landsat series of satellites and perhaps Sentinel-2. Both of these carry multispectral measurement instruments. So we work, if we're using multispectral remote sensing, we're working in the visible, near infrared, and shortwave infrared part of the spectrum. So about the part that I've highlighted here in the illustration of the electromagnetic spectrum. So why do we use this range of energy in different parts of the spectrum? So if we look in the visible part of the spectrum using remote sensing, so this is an image from a sensor which was measuring in the visible part of the spectrum, what we can see is essentially an image that would look similar to if we mounted a classic camera on a satellite. So what we would see with our eyes, all right? So we can already get a lot of information from here. We can see this is probably vegetated area because it's a bit green and things like that. So the reason we use different parts of the spectrum is that it's going to highlight different aspects of the land surface. So for example, the next image here, this is using information from the near infrared, and the near infrared part of the spectrum is represented here in shades of red. So the redder areas have a higher reflection in the near infrared from this part of the land. And what we can see here is it really highlights green vegetation. And so this kind of difference between what we observe in different parts of the spectrum is what we're going to be looking for in analyzing remote sensing data with multispectral data. So if we look in a little bit more detail, what we use are called reflectance curves with multispectral remote sensing data typically. And this tells us for each type of land cover and each wavelength, how much of the incoming radiation is reflected. So each land surface will absorb a certain amount of radiation at a specific wavelength and reflect a certain amount. So if I follow, for instance, the curve for green vegetation, I can see that if I'm measuring in the blue part of the spectrum, I'm going to have a relatively low reflectance. If I measure in the green part, it's a little bit higher. So that's also why we see it here green, because the visible we're using the blue, green, and red, so the green is the dominant. But if I keep following this curve, I can see that if I'm looking in the near infrared, I have a really high signal. And so that's what's seen here in this image with the near infrared, where the red part is really highlighting my green vegetation. So by using this knowledge we have about how different surfaces interact with energy in different parts of the electromagnetic spectrum, we're going to learn a lot about our land surface. So this is what, for example, land classification products are based on. So of course, we don't only have multispectral remote sensing, we also have different types. I won't go into too much detail about them today. I wanted to highlight thermal remote sensing. So this we look a little bit further right, so a little bit longer wavelengths. This is the thermal infrared part of the spectrum, and this gives information about the land surface temperature. So this is again the same image, visible, but now thermal infrared. And so here the part that's white is a part that's warmer. So it can be a bit surprising. Here we have a warmer river than what's around it. But this is actually an image from a thermal power plant in Iceland. So we can see that by looking in this other part of the electromagnetic spectrum, I'm getting additional information about the land surface I'm observing. If we move further in the spectrum, and again, I'm not going to spend a lot of time, this is just to give a bit of an overview of what's done or what's possible. We can work in the microwave part of the spectrum. In the microwave part of the spectrum, we start to look at both active and passive measurements. So, for example, using active, so that means, again, the satellite is emitting energy in the microwave part of the spectrum and then capturing the reflection. We can get information such as water levels or land surface levels as well, so digital elevation models. And we can also get information about flooding, but we won't go into detail about this. So the image look a bit different. You can see they have some very specific characteristics that are linked to the microwave, to the measurements, basically. They have a bit more complex interpretation, so there's been fewer applications so far, but it's really, I think microwave remote sensing is one of the very fast developing fields at the moment in remote sensing. Finally, I just want to also mention briefly, because maybe some of you have heard about this GRACE mission. So this is a satellite mission which uses gravity and looks at changes in the gravitational field of the Earth at the seasonal scale, because these changes are dominated by changes in where the water is stored, because changes in where the water is stored will create local changes of mass of the Earth, and this will be translated into changes of gravity. However, this has a very coarse spatial resolution, and I guess this is a good transition to my next slide, which is about what characteristics we want to take into account when we look at remote sensing. So when we're starting to work with remote sensing, there's really two main characteristics we want to take into account, which are the spatial resolution of the data we're working with, which is the size of the pixels. So an image with high spatial resolution will have very small pixels and allow us to see a lot of detail. And an image with low spatial resolution will have larger pixels and will show us less detail. The other important thing to take into consideration is the temporal resolution, which is going to be the time between two measurements at the same location. And this will depend on the satellite orbit, because of course it takes time for the satellite to complete its orbit and to come back to the same place. So the little animation in the bottom shows the time it takes for a series of satellites working together to create a global precipitation product. And it's illustrating the time it takes for them to cover the whole Earth by using their orbits. So what type of resolutions do we have to work with if we work with multispectral data? So two of the main satellites that are currently used, as I mentioned, are Landsat and Sentinel. And what we can see is that, so the Landsat satellites, they have, for most of the data, for the multispectral part of the data, have a 30 meters spatial resolution. And the revisit time is every 16 days. So this is very important to know, because if I'm trying to measure something that's much smaller than, or around the size of the 30 meters, and that happens at a quick time scale, then maybe it's not going to be appropriate to use this data. The Sentinel data has a higher spatial and temporal resolution. And the way that it's achieving this higher temporal resolution is that it actually has two satellites flying in formation to be able to give us this higher revisit time. We have other satellites which can give us higher revisit times, but typically that's going to be accompanied by a lower spatial resolution. So you often have these trade-offs between temporal and spatial resolution when you're looking at satellite data. Okay, well, this is just a nice picture to show a bit how that looks if you're looking at an area. This is an irrigation area near a river in Zimbabwe. and just to give an illustration of what the difference between using Landsat and Sentinel can be. The data that we're going to use when we are, beginning with remote sensing, or even if we're been working with it for a long time, but we're working with applications, we're not going to use the raw data that comes directly to the satellite. Typically, we're going to use data that's already been processed to give us some nice consistent variables in these nice rasters with square pixels. So the reason I'm highlighting this is that all this processing can introduce, different sources of uncertainty, for instance. Because I've been talking about all the advantages of remote sensing, but we also have a number of complications, a number of challenges in working with remote sensing. So this image shows, for instance, the percentage of time an area has cloud cover. So we can see that the areas that are red have nearly constant cloud cover. And some of the data sets that we work with, in particular, this multispectral and thermal data, is quite affected by clouds. It's actually one of the advantages of using microwave data, and why we go through the trouble of dealing with that data. One of the reasons is that it will allow us to see through clouds. So here, for instance, you can see that if you're working in these areas, you're probably completely fine. But if you're doing work in some of these quite, equatorial areas, you might have a huge challenge with using data that's obstructed by clouds. So I can see I'm going a bit slower than I wanted to, so I'm going to be a bit quick on this, but it's just to show again, of course, we have our source of radiation, which can be the sun or a satellite, and then we have our sensor. What we're interested in is basically what comes directly either from here or from here. But we can see that our sensor is also going to be capturing what's intercepted by the clouds, what's scattered by the atmosphere, and so on. So that's just to highlight some of the difficulties that can occur when we're working with remote sensing. If we look at why we want to use or why we don't want to use remote sensing, there's a number of benefits which I've already highlighted for satellite remote sensing. But there's some things that are really nice with in situ data. So we can get higher temporal resolution, for example. So if I place an instrument somewhere, I don't need to wait for a satellite to come back. I can measure every minute if I want. I can place my station exactly, where I want to make my measurements. And also what's important is I have a lot of direct forms of measurement. So it's a bit more related to what maybe I really want to measure. So we have, for instance, precipitation products from remote sensing, but we have to get to the precipitation by interpreting, the reflectance of clouds and the condition of the atmosphere, etc. Whereas if I put a gauge, it's more direct. I see how much rain has accumulated in my gauge, and so on. But what I want to highlight with this and putting some positives and negatives is that when we want to work with data, it's not always that it's not that we can really find a winner because we're between remote sensing and in situ data, because it really depends on your application. And what's best is to find a way to work with both types of data to have complementarity of the data sets. And then as a little joke, I guess, I also add that we haven't figured out how to do surveys from satellites. So of course, if we're wanting to do remote sensing for communities, which is the goal of our project, we can't, of course, and we don't want to rely exclusively on the data that we can get from satellites. Here I have a few examples of data portals from which we can obtain data sets to work with them. They're actually quite easy to use overall. I won't go into detail about them here. I've made a short video. I guess I could have maybe accelerated it a little bit. Need to figure out how to start it. Okay, I can't figure out how to start the video, unfortunately, with the laser pointer. So I will just, oh, here it is. Now it's finally starting. Okay, so it's just an example of how to use one of the data portals. So this is the one from Copernicus, which is a European a data provider. And here what we're going to do is look at how we can easily find some Sentinel-2 data So this is for the area which I think we're studying with our Ati River case study. So what I'm showing here in the video is we can choose the different types of data, and then we can pick the date where we want to look at the data. And so here, for example, I'm loading the latest date. So that's was from the 14th of October. So you can see it's very recent. It's just from 2 days ago. And I did this yesterday. And we can see the frequency that we can obtain by looking at the time. And here they have already some products which are already made. So for instance, here I can already select the NDVI. So NDVI is an index you might have heard of, which is higher for densely vegetated and healthy vegetated areas. So you can already use some of these pre-made products that they have to analyze your area. And then on the side, because I know that we're interested, for example, in looking at encroachment in the swamp. So here I'm just showing that you can very quickly select data over a time period. So the Sentinel-2 data, this one started in 2016. So I'm making a small time lapse here that starts in 2016 until 2024 with one image per year and a selection criteria on how much cloud cover I'm allowing my images to have. And now you can see on the screen how the evolution that is happening. So here we can see, for example, this area got a bit lost some vegetation cover over the time period. So this was just to illustrate how easy it can be to access this open source data. So we're starting this project now, but like this, we can already have access also to information from the past 8 years very easily with a few clicks. So I'm going to close on this. I'm already way over time, so apologies for that. And I will stop sharing my screen. And if there are any urgent questions, we can take one now. But otherwise, I'd like to give the floor to Elga, and we can take questions in the discussion later. Elga?
Yes, hi, start. Can you hear me?
Yes, yes.
Yes, hi. So let me share my screen quickly. Can you see it?
Yes, we can see the screen.
Yes. So also a big welcome from my side. Thank you very much for joining this first webinar. And the idea is that I continue this presentation on the basics of remote sensing by looking at what we can measure. I think we had a very nice introduction from Claire, so thank you very much for taking us through a tour from initial measurements to satellites. Also, she went a bit in depth about the physics behind, so the energy and how this energy is emitted or monitored using sensors. And then we also looked at some of the images that we can obtain from remote sensing products. But what I want to talk about, it's also, okay, very nice, but what can we do with it? What can we actually measure from remote sensing, which is of value for our project in our field, for water resources management, and what can I do with this type of measurements? I took part of this presentation from a course that Claire is giving to students. So she's kind of guiding them through the water cycle. I think it's a very nice idea to explore the different remote sensing derived products that are available through this. So I will go quickly through that with little details. So it was a bit challenging to condense all this different information in such a short time. So it's more of to get an overview of what is there and also for us to reflect on what is interesting and what we can use then maybe or discuss more in details for the coming webinars. And I also decided to put some examples from the work I do. So I think most of you already know me, but I didn't introduce myself. I'm Elga Salvadore from IHE Delft. I did a lot of work with water accounting and I'm more of a user. I understand the data and some of the physics, but I'm not really working on the production of remote sensing data or I'm more from the user perspective. I use it for my application, for my modeling. So I have a bit of an overview, but we can also discuss together with colleagues more in depth about the specifics of different products. And then I also put an example about my PhD, something I did, I don't know, 10 years ago. It was nice to look back at this type of work. So the first component, I think, is the precipitation, which is something we all know it's very important. It's the main driver of the water cycle. So it's the biggest component. It also has a high spatial and temporal variability. Normally we measure with rain gauges, and Claire already showed this image showing that we need some spatial interpolation. You have many points, and also this network of gauges is shrinking over time. We actually have less in situ measurements. It gives us a motivation to explore other type of measuring techniques. And one is, for instance, using ground-based radar data. I think some of you might have heard about. And it's providing spatial information at a high spatial resolution, temporal resolution, through also it's remote sensing, but it's also very localized. So the difference between this type of and satellite is actually only available in certain locations. So we might not have this type of measurements in the regions where we want to work for a project. So one option is to use remote sensing derived precipitation. I will not go so much into detail, but it's you have many different algorithms to estimate precipitation using remote sensing techniques. And some of these algorithms already include in situ data in their processing. And they provide validation of the data sets. Of course, they can only do this where there are in situ data. And because they are globally available, they might be very accurate in some regions, but a bit less in other regions. They are quite widely used, and we use them for monitoring purposes, but also as input for hydrological model, hydraulic model, so for flood forecast, flood modeling, and so on. We have many different products, and these are a little bit the characteristics that Claire was explaining before, what we need to look at when we choose the data. And then in this table, we summarize an example of 3 of the, I think, most commonly used precipitation products. And then you can see they have different temporal resolutions. So if you need to have information in one location or one pixel every 3 hours, you have that opportunity. If one day is sufficient, then you might also consider other data sets. And also what you need to consider is where geographically you are located. So it's global or near global, so not all the products cover the entire globe, and then the period you're interested in. So some cases you can go back up to 1980s to now, and you have different spatial resolution. You can see it's pretty still coarse. So you have one value of rainfall every 5 kilometers, for example. And in this case, chips also provide, it's one of these products that also takes into account in situ data. Then we have the evapotranspiration, which is the second largest component, and we often refer to it as water consumption. So we're interested about how much of the water that we have on our land and from the rainfall is evapotranspires and goes back to the atmosphere. So with evapotranspiration, we define the amount of water that is evaporated by surfaces or transpired by plants. And this, it's quite hard to measure in the field, and there are very few stations. It's also not a direct measurement even in the field, but it's very crucial for monitoring vegetation and monitoring crops. So it's something we really need. There are different methods, again, to compute ET. I think one of the most common is the energy balance approach. And for that, you also need a number of remote sensing inputs. So for instance, we will need land surface temperature, which is something Claire discussed before, and also NDVI, one of these parameters. And this is a bit how it looks like. So you have maps, like global, this is a global product for evapotranspiration, where you see, in this case, how many millimeter per year of evapotranspiration, actual evapotranspiration, were recorded with this technique in a certain period of time. So it's an average of number of years. So you will see in some locations you have up to 1,500 millimeters, these violet zones, or in the red part you have very little evapotranspiration. And this can be because there is little water availability, or because the desert conditions or arid countries where you don't have vegetation. You have, again, choice of multiple products. One of the newest developed is probably the Vapor version 3, and you have data every 10 days on evapotranspiration at 300-meter resolution. So you have pixels of 300 by 300 meter. But it's only available from 2018. So you see it's a little bit of a newer type of product compared to precipitation. So you only have about 20 years of data, which is probably a lot more than what we have in terms of in situ measurements. Another interesting component of the water balance in our case is the surface water. So we can get a lot of information about location of water bodies, the elevation, so how much, let's say, the water levels in certain conditions. So there, for instance, one good example, which I like a lot, is the Global Surface Water Explorer from JRC. And there they have developed surface water maps using Landsat data. So Claire mentioned there is, you have many different Landsat missions to ensure continuity. So they started already 30 years ago. So we have 30 years of data where we can look at how things have changed. So I looked, for instance, also the other day on this portal, and one of the products they provide is water occurrence. So you can look there and see, for instance, in blue zones, there was always water in the past 30 years. So it's more of a permanent water body, while in other location you only have a certain percentage of the time, a number of months in this period, or a number of years where you had water, and other majority of the time was actually land. You can also compare the distance past with more recent past, and then see if you have a change. So you can also try to look at, okay, is my water body, in this case a lake, is it expanding, is it contracting, and use that data to understand the changes related to other conditions. That can be meteorological condition, can be human-induced factors, and so on. What is also, and it's all open access. The same you can also do looking at water level variations. And one database which is very nice is the DAHITI is called, Database for Hydrological Time Series of Inland Waters. And therefore, a number of water bodies, both lakes and large rivers, in some location you can have, you can obtain the water level elevations. So in this case, I was looking at Lake Victoria, and I just extracted the time series of this elevation, and then I can clearly see what we already knew. So there was an increase in the level, actually a few meters of increase in a period of about a bit less than 20 years. Another interesting thing you can use remote sensing for is to look at water quality and derive water quality indicators. So we know that water quality can affect some of the chemical but also optical properties of water. So we use optical and multispectral, particularly multispectral remote sensing for this application, which is something Claire really discussed in details. But you can also look at the temperature of the water as a parameter for looking at water quality. So thermal infrared can also provide information there. You can do more of a qualitative analysis and then look at how your reflectance, so how much of this energy, solar energy, is reflected back, is changing over time, and maybe these changes you can relate to the quality of the water, or you can do more a quantitative analysis if you want to quantify what are the components and the changes there, but then you need to do a lot of probably sampling, and there are some empirical equations that you can use. To prepare this presentation, I also had some fun to look back at my work when I was a PhD student. And at that time, I was trying to use remote sensing to characterize aquatic vegetation. And my case study was in Belgium, in Brussels. And there you have a lot of small ponds. So it's, in a way, semi-natural because it's still part of the city, and they have a lot of problems with eutrophication and pollution. So the idea is that can we actually monitor these components using remote sensing data? And the idea is also that you want to find ways to, it's probably expensive to do field surveys. So if you could actually use some satellite data to identify locations of blooming of algae and so on, could be a good technique. So there they have problems also with what they call it cyanobacteria that can be harmful for the population. So they want to invest in doing to improve the ecosystem and to restore the conditions. So what I did was to look at some hyperspectral data. So Claire mentioned the multispectral, so you have multiple measurements at different locations in the spectrum, but you also have sensors, which we call it hyperspectral because they measure at many more wavelengths. So they provide a much more detailed information of the response of surfaces. Now, because the challenge there to look at vegetation in inland waters is that in general water is absorbing a lot of energy, so very little is reflected back. So you need a bit more detail in the measurements you do. And then the idea was we were trying to discriminate, to make a differentiation between ponds and lakes with algae, with cyanobacteria, and with macrophytes. And then for that, I did a lot of remote sensing, but in the field, so in situ remote sensing measurements with different sensors. And I created reflectance curves. So this is the figure Claire showed as more of a theoretical, what you expect from the reflection to be for vegetation or for bare soil and for water. So here you also see that reflectance of water body is very limited. And then with these sensors, we actually have a lot more details, but they are less clean as type of reflectance curves. So by making many different measurements at different location and knowing which type of if algae were present or cyanobacteria were present, we try to group them and then use this information to classify our image. And then the idea was, okay, our conclusion was, okay, it would be possible to differentiate and then create maps for that purpose. Now I'll try to, I think we are running a bit out of time. Other important things that you can use remote sensing for and they have derived products for are also, like in my case, but in general, more land cover application. So I think most of you have heard about land cover maps. I think there is an effort to also make globally available land cover maps. There are a few nowadays that provide information every 10 meters. So for the year 2020, 2021, you have maps available at 10-meter resolution. They might, as you see, they have only a limited number of classes. And if you want more information or you want to differentiate between different crop types, then you have to do probably some classification yourself using Sentinel or Landsat data. Finally, to conclude, the last application I have in mind is something I have work with is to look at maybe the use of remote sensing in agriculture. I'm not an agricultural expert, but I was trying to interpret some of these global products for agricultural purposes. And then, for instance, this is the case in Cambodia. And then I was looking at the reservoir, and this reservoir serves a particular command area. And in this map, you can see the evapotranspiration. So you can already see that there is quite a large variation of water consumption within a command area. And this is something I can look at the spatial variability using remote sensing and also try to quantify how much is the total water consumption for one particular area. This is using a global product. So you see the resolution is coarse. And then when you want to zoom in and do a more detailed, in-depth analysis, perhaps these global products are not sufficient. So what my colleagues from the International Water Management Institute did was to use primary data to calculate the evapotranspiration. So using remote data to estimate the evapotranspiration at a finer spatial resolution. So here you can see that there is some consistency with the global products, but here you have a lot more detail. And then you can see that some areas consume some more water than others, and very often is the location which are close to the main canals. So the further away you go, the less water is available. You can also, with the same model, try to estimate the production. So you can create maps of the water yield. So in this case, rice. They have calculated the tons per hectare for every season. And then you can see also that there is quite of a large variability within one irrigation scheme. So some plots, some farmer can produce up to 4 times other farmers in the same region. So you can use this spatial information to query why these changes are happening. And if it's about variety, soil properties, the practices, or if it's also related to the lack of available water in critical moments in time. And then you can combine these two information, so the production and the consumption, to calculate some of these indicators that we use very often. So the water productivity, which is the ratio between production and consumption. And then you can see the blue zones are locations where you, for the same amount of kilograms produced, so you produce up to, I don't know, 1 kilogram of rice every cubic meter of water, while in other regions they need a lot more water or they produce a lot less. And then you can use this information to understand what is possible at a local scale. So you will have an average of this crop water productivity, and you will have farmers achieving actually higher values, and you can use that as a target to try to improve to some achievable objective of improvement and become more efficient in the use of water. I think this is about all I had in mind to present for today. It was a little bit, I feel a lot. I hope that can help us to have a conversation and a discussion and lead to some ideas on what we can use for a project or what we can investigate more through our research.
Thank you very much, Elga. So I think both Elga and myself were a bit ambitious with time, but it's very hard to compress all the things we wanted to share in these short presentations. So I'm going to already suggest that we extend the session by maybe 15 minutes, so we have at least 20 minutes for the discussion. Of course, if anyone needs to leave because you had prior engagements, please do. But we can start already with some questions. So we have the members of the team here. I know a few of us have a lot of expertise with remote sensing. I'm thinking in particular of Abebe, I think, who is also here. I also invited our colleague Vinit Kumar, who's a new colleague at IG, and he's an expert on topics that we didn't touch on too much, on I think microwave remote sensing, in particular for vegetation, if that's right. So I think that would be very interesting. Yeah, thank you. So thanks for joining us as well. Yeah, so at the start, I'd just like to open the floor for questions. I know it's a lot to take in. Yeah, then maybe I'll just start with one question actually for Vinit, since we haven't covered so much of the microwave for vegetation. Maybe you could give us just a very short, a few minutes, introduction to what we can do with that. What types of resolution? What are you observing with the microwave? Is it completely different? Just to give an idea of what's possible.
Yeah, okay, thank you, Claire. Maybe I will take just few minutes only. So, like the presentation which Claire and Elga gave, so they talked more about the optical part and the somewhat hyperspectral part. But in microwave remote sensing, I think Claire mentioned that it's having passive and active part of microwave remote sensing. So where in active, the energy is coming from the satellite, it strikes with the ground and it gets again reflected back to the satellite. So there are certain advantage with the active microwave remote sensing. So the one thing is like during the cloud period for tropical countries or countries where they have monsoon season, so it's possible to see the data below the cloud. And also, so for example, the country like India, where rice is grown during the monsoon season, and if we want to do the crop acreage estimate, so with optical, it's challenging because we don't have the frequent data available. But with the active microwave or synthetic aperture radar, SAR remote sensing we call, so it's having the data during the monsoon season. So the data continuity remains available all the time and it is not affected by the environmental condition. Another important property of microwave, so they interact with the target in a different way than compared to the optical. So they interact with the geometry of the target. So for example, if you have a leaf, so leaf from rice or wheat, or if it is a leaf from banana crop, so the size is different. So it affects the amount of energy which is reflected back or back scattered back, and the water content. So in water content in the target and on the target. So we called it dielectric property of the target. So uh, the amount of energy which is reflected depends on two properties. One is the geometry of the target and the dielectric property of the target. So on that basis, we can actually distinguish, for example, various crops. So let's say we can distinguish rice and wheat and banana or all those sort of, because they have different structure and different water content. Also it is affected by with what angle we are looking, what is the polarization, so what is the characteristic of the system or the satellite. And yeah, and so it's very useful, and also it can penetrate into the soil, so up to few centimeters. So let's say depending on the wavelength of the satellite we are looking, so it can penetrate up to 5 to 10 centimeter. So we have the information about the soil moisture. So that's how remote sensing is used in vegetation and agriculture and water related applications. So majorly crop classification, soil moisture, biomass, those kind of biophysical parameter estimates. Yeah. So
Okay, thank you.
yeah,
I think
thank
it'll
you.
be very interesting for some of our case studies where um, for the pastoralism case. So we have two studies there, and we're going to be wanting to look at some, yeah, the health of the pastures
Yes.
where the animals are meant to go graze. So I think that might be some very interesting data
Yes.
sets to keep in mind.
Yes. Yeah. So we can get information about, for example, water stress in the
Hmm,
crops. That's
great. Thank you.
yeah. Thank you.
Violet, I see your hand is up.
Yeah. Yeah, first is to just say thank you, because now you're giving us very useful information about how we can, what is possible, so that it stretches our imagination about what we can do. So for one of the, within the Athi River, one of the cases we are looking at is it's not a very big swamp. It's like 3.7 kilometer perimeter. But it is a swamp that it's not clear what is its depth. And then it's also not very clear what feeds it. Where does the water come from? But that swamp it has a river that flows out of it. And during the dry season, this last drought, we had quite a severe drought in 2023. The river that flows out of it completely dried up. So it really affects the communities who use the river downstream to grow their crops. Then now during the wet season, we had quite heavy floods. The river is flowing. So what we wanted to know is, like with remote sensing, can we even know the depth of such a swamp? Because it's not very clear. How can we get to understand that swamp more so that the community living right around it, including ourselves who draw, we get water from it, can start seeing that this is not an infinite resource. It is finite, and you need to look after it. You need to control abstraction. The abstraction now, there's a lot of pumping happening from the swamp, and that's why during the dry season it had dried up. So that kind of the kind of data that remote sensing, and even because you guys have all these expertise, even hydrological data that can help the community have a conversation. We have a conversation among ourselves. How do we look after this swamp so that we don't kill it? Also, can we know the levels of eutrophication that has happened over the years? Because the farmers push soil into the swamp to grow crops. So those are the kinds of questions that we would like, because those questions can then help the community to sit and say, hiya, our swamp, we're finishing it. This is what we need to start doing to change the way we are using it and abusing it. Yeah.
Thank you, Violet. Very good questions. Does someone want to give a first answer? Should I begin? Okay. I'm not sure how to. Okay, I'll just begin, and people can also answer in the chat if you have additional information or somehow indicate that you have also an answer to give. So in terms of some of the questions you asked, it will depend a lot on the nature of the swamp. So I believe it's a vegetated area, if I'm not mistaken.
Yes, it's what is called a quaking bog. So it has a layer of vegetation floating. So when you walk on it, it feels like a sponge. Yeah.
Okay. So in terms of the depth from remote sensing, I don't think that's going to be possible from a direct measurement. And anyone who would have contradicting information, please feel free to contradict. This is not. However, if the extent is also varying, this is more what we can see from remote sensing. So also using some microwave data or optical data, depending on the character of the swamp, we can see if there's some extension or loss of area. And the loss of area, if it's flooded, for example, we can also see that under the vegetation with remote sensing. So that can be some powerful tools. But indeed, as you say, in terms of really understanding the full functioning, it's not going to be sufficient on its own. We're going to also probably need some field data to complement our remote sensing data, perhaps also some modeling. So you mentioned, for example, that it's unclear where the water comes from. So if it's fed from some underground, some base flow, then it might be challenging to see that with remote sensing. So I think I'm very happy you said that this stretches a bit your imagination, and I think that's something that we'll really have to work together, looking at the specific area to understand how best to contribute. I don't know if anyone wants to add something. You can unmute and.
Can I?
Yeah, Elga?
So I was thinking also when Violet, you mentioned that there is, so you want there is some changes, so in the level of eutrophication and the fact that you have maybe farmers using part of it and so on. So that's also those changes. There's also something you may be able to see. depending in which time frame, but then we could look in the past and see how the land has changed there.
Yeah, and I think,
Yes.
yeah.
Mhm. Yeah, because that it has been changing over the years. There's even a major road that cut a part of it. So it would be interesting to see over the years what has happened to it. And the communities living around it, some of them imagine that its water can never run out. They have this, they just see, they've always seen it have water. So they don't have their imagination, they can't stretch to where it does dry up. So it would be good, it would be interesting to be able to tell them that actually it is going reducing in its volumes of water, whatever, just to get them to take it more seriously. Yeah.
Okay, thank you, Violet. I see Giselle, you also have a raised hand. You may unmute.
Yes, thank you to all the presenters for interesting presentation. Get many information from all you shared with us. She said that I usually get shape files and extract just values from them, so I don't have much information about remote sensing. I wanted to know, I think it's the presentation by Elga, where you mentioned soil water, that we can get information about soil water quality. And I wanted to know what are the different indicators of water quality that we could get. Also, another question for me is to know if it's possible to get, I know Vinette mentioned that in agricultural field, you could get some information about the soil composition at some level. So I wanted to know if for forest areas, for instance, it's possible to get information about physical or some chemical component of the soil. And as it was mentioned a bit, that with remote sensing images, you could, or products, you could identify the type of crop. I think you need to mention that. And I was wondering if there are any improvements that could be applied in the forest area, maybe to identify some genus at genus level, if we can go to species level, for instance. Yeah. So I think those are my questions, but one thing I was wondering about is how is the wavelength measure? How to get that? Just curiosity. Thank you.
Should I start? So thank you very much for the question. So I think you mentioned a few points. At the beginning, we were talking about soil water. Like you mean the amount of water in the soil, like the soil moisture type of, or the root zone soil moisture?
I mean, like soil moisture in the soil, depending on the depth of the soil.
Yes. So we didn't talk much about, I just briefly mentioned it. There are some products available. They have, however, quite of coarse resolution, so the pixels are quite big, and they can only penetrate, let's say, the first few centimeters of the soil. So it's not that you have the entire column. So I don't know what is your application, but like in my field, what I do is I do some hydrological modeling, and usually what we're interested is in the unsaturated zone to know how much water is there. So for that, you need some, let's say, additional modeling, but I think it's still worth to explore. So maybe I could add some links also to products related to that in the presentation. I think they will be shared, right, with the team members. And then you were mentioning water quality indicators. It's also not my daily bread. I mentioned a few things, but I kind of stopped looking at water quality 10 years ago. So I think in between, many things have been done. So what I know is that you have, so it can be used to, so we use remote sensing to look at if you're looking for differences in color mostly. So the turbidity, for instance, so if you have, they use it at the deltas of some rivers, or because of human-induced activities, then you have a release of movimentation of sediments. That's something you can probably map quite well. Some indicators related to quality, like spills, if that affects the color of the water, or other, like eutrophication. So you see the changes there as well. And I'm sure there will be many more different parameters that maybe we can look it up together. I don't know if your colleagues have, or other experts in the room.
I'm
have something
wondering
to
if
add
our
to
colleagues
water
from
quality.
Lake Tana, if you're also working with lake quality, maybe you have some things to add. Maybe the experts are not, or they're going to become experts in the course also. I know that working on the water hyacinth, for example, that's the main goal of the Lake Tana study.
And I think we also plan to have probably a webinar specific on water quality using remote sensing, so that we will invite also like experts in the field.
And you also asked, so I don't know if Vinit, if you have anything to add on the soil moisture.
Yeah. So, thank you for your question. And just to add on, yes, with microwave remote sensing, it's possible to have surface soil moisture, like as I said, the top layer of soil, not the root zone kind of soil moisture. Also, because you ask the physical and chemical property of the soil under forest canopy. So then it's very, so first thing, microwave, we can't get the chemical property of the target. We can have some physical property, not the chemical. So, but it is under, if it is under forest canopy, then again it will be because the penetration is although very high compared to other remote sensing technique, but not as high that we get very accurate soil moisture information under the forest canopy. So that is, I think, the limitation part. And then you ask, can we differentiate the genus and species level in the forest? So with the microwave, we can go like discriminating like coniferous or deciduous, that kind of level, but not at a species level. Maybe with the hyperspectral remote sensing, because they work on species level uh, uh, classification of vegetation. So that could be one of the possibility. Also, for example, if you want to know the carbon content in the soil, that is also with hyperspectral remote sensing the possibility, but not with the microwave.
Great, thank you,
Yeah,
Vinit, for
so
these
yeah,
additional precisions.
yeah, thank you. I hope I answered to Giselle question.
I think I saw most of the things answered, but Giselle, if you have more, you can.
No, I think I got my answer. Thank you.
Okay, great. Maina, also, you have your hand raised if you'd like to ask a question.
Yes, thank you. I hope you are able to get me.
Yes, we are.
Thank you all presenters for the nice presentation. It's an eye opener, and the power of geospatial to different applications. So I would not ask a question to a specific maybe speaker, because the idea is we have experts here. I'm not a good expert, but at least I have interacted with the geospatial the remote sensing. So my question would be, I might have some interest in looking at water use efficiency, especially within the Tana. And the evapotranspiration has been mentioned. However, I would like to know the spatial resolution, because some of the crops which are grown within the area of interest, they are not large-scale farms, and there could be several kind of plantations, not really plantations, but several farms which actually contain several kind of crops. So, and also at different growing stages. I'd like to know how possible that one can be. And then the other thing which have actually been mentioned by my previous colleague who asked some question on the water quality in terms of the parameters which can be actually captured by remote sensing. I think I would later have either an answer for now, if not, so maybe in the next upcoming maybe webinars, because I would also like to relate that to the in situ measurements, so that at least you can compare maybe and improve on the accuracies of that. So maybe for now, I can ask those two questions. Thank you.
Okay, thank you for your questions. Yeah, I'll start with the water quality question. So a lot of as Elga mentioned, we can do some, basically, if you want some quantitative measure, typically you need to get a lot of field data and build, a data-driven model where you relate what you measure in the field to the spectral information at the same time. So you have to do some measurements that are timed at the same time as the satellite overpass, because of course these things can be very dynamic, so that you can then relate the reflectance to what you have in the field. I have a list of things that have been done. Of course, once again, it's not my specialty either. So some of these uncertainties, I'm not exactly sure. I know that there's one that's very commonly done is chlorophyll A. Also turbidity, as Elga mentioned. But people also use it for, color dissolved organic matter, total suspended matter, salinity, and all kinds of different things. But then, there's two challenges. So one can be that sometimes these water bodies or rivers we want to look at are quite small compared to the resolution of some of the data we have, because the instruments that have the best capacity to look at quality are these hyperspectral instruments. So we need to measure in more parts of the spectrum, and these tend to have a lower spatial resolution. So they will have maybe, a couple 100 meters spatial resolution. So we have to start looking at the bigger water bodies to be able to have some good information. So that would be one challenge. So that's on the topic of the water quality. We can, of course, I can share also some other information. There's a lot of great resources online for all of the different, remote sensing topics, but we can also try to find some experts to come to meet us in some of the next webinars. The water use efficiency. So Elga talked about some of the global products. If I'm not mistaken, you're in Kenya, Peter?
Yes, I am.
Okay, so with WAPOR version 3, over all of Africa, we have 100-meter resolution. And that's the highest resolution sort of readily available product. However, as Elga showed in her slides, you can use some models that can for your specific area of interest be used to produce higher resolution ET data. So one example that we've been teaching recently at IHE is called PyWapor. So it's basically you run the WAPOR algorithm, but on higher resolution data than the one used for the global data set. And you can get, I think, 20-meter resolution ET from this model. So that can help to look at some more detailed analysis on smaller scales.
Thank you for the answers. Maybe we can, after this, maybe we can get contacts so that we can engage further on the specific subject. Thank you.
Yes, that sounds good. I don't see more hands right now. Earlier, Shaul, you had your hand. Oh, I see Gohao has a hand up. Please go ahead.
Yeah, thank you very much, Claire. I would like to ask you one question about the Digital Water Africa initiative. This Digital Water Africa initiative.
Yeah.
There are also resources, I think, under the Digital Water Africa. For instance, you can easily extract remote sensing data also from this database, I guess.
So I haven't worked so much. Are you talking about the Digital Earth Africa, perhaps?
They call it DIWASA, Digital Water.
Okay, I haven't actually worked with it. So if you want to put a link maybe to share with everyone in the chat, I think that would be very nice because it's true. There are many platforms.
Yeah.
Maybe
I think you are right. It's the Digital Earth Africa. You are right.
okay.
Yeah.
So I'm not involved in that initiative. I have heard of it. Did you want to?
I think I have brought the issue. Probably it can be as an open resource for remote sensing users as well. I don't have actually much information about it, but I heard from International Water Management Institute staff about this.
Yeah,
I think we lost Claire.
Yeah,
but
yeah.
yeah, I think we need
Yeah, so Koshu, I think yes, the first which you mentioned, Devasa, is from International Water Management Institute, but the other one is Digital Earth. It is also from other agencies and where they are keeping data in a queue form, and we have lot of, let's say, automated NDVI kind of or a set, so analysis ready data product kind of information. Yeah, so thanks for sharing that. And if we need, we will look the data from that Digital Earth Africa source.
If I may add just on about the Digital Earth Africa, it's also a collection of tools to analyze remote sensing data to get access to the data is one thing, but also there are a collection of notebooks which help to analyze and extract useful information from satellite data. And at the same time, also you can get a kind of a computing access, like a computer, where you normally analyzing remote sensing data requires some kind of resource, computing resource. So people who may not have access to that kind of resource also can register there and get a kind of a virtual computer to do their analysis.
Yeah, thanks, Solomon. Yeah, it's a more of like cloud-based resource as well where we can process the data. Thank you.
Yeah, I'm just trying to see if Claire can join the meeting again.
I'm
But
back.
yeah.
I was
I'm-
also thinking.
Can you hear me?
Yes.
Okay, great. So thank you for taking over. Go ahead, Olga.
Now about Digital Earth Africa, I also didn't know much about, but it's also something we know colleagues that were involved in the development. Because I think Lisa Rebello from IMI is part of that. So it can also be, if it's of interest, that we invite someone for a talk.
That would be good. Yeah.
Okay. So we are about a half hour over time, but thank you everyone for staying. I think it was very nice, and maybe we'll schedule an hour and a half for our next webinars because it's good to have time for questions. So I'm going to ask once if there's a last question that anyone wants to, or comment, or anything that anyone wants to bring up. Okay, then I think we can perhaps close the session. Thank you so much for attending and for the questions. And we know it was a lot of information, so I'm guessing more questions or ideas might pop into your head, in the next few weeks, especially for those for whom this was one of the first, exposures to a lot of what can be done with remote sensing. So please don't be shy about reaching out to us in that case. So I want to thank everyone for joining. I also want to thank Vinit for joining. I'm trying to convince him to join our project also. Let's see how that goes. And we have our next webinar scheduled in 2 weeks, and we'll be sending out the link soon. Thank you, everyone. Goodbye.
Thank you. Thank you.
Yeah,
Thank you.
Yes, and we will put
Bye.
the presentations. Perhaps, Elga, we can put them on the WDPP repository and share that link
For the
with
recording as well.
everyone. Yeah, perfect. Thank you very much.
Thank you very much for organizing such important.
Thank you.